Yeah, I'm doing dentistry. No. Why are you trying to set your sister up for torment? Okay. No, I'm doing dentistry. All righty.
No. No.
This is the part of vectors you're probably going to really want to pay attention to. This is how you're going to solve all your systems. I showed you the geometric representation of vectors, but this here is how you're going to start to break things down. So so we've been talking about how to find vector components. Now, talking about adding and subtracting vectors using vector components. So, I mean, what if we have vector A and it has components AX and AY, and we have vector B and it has components BX and BY. The addition of these two, if we say that A plus B gives us vector C, that means that the components of CX is going to be AX plus BX, and CY is going to be AY plus BY. So when you add together the vectors, you add their individual components together. Last semester, for some reason, a lot of people wanted to start adding X and Y together. Don't do that. Those are different dimensionally. Now, what if we had A minus B is vector D? So the X component of D this time is going to be AX minus BX. DY is going to be AY minus BY. So they're done in the same way. It just depends on if you're adding or subtracting. Which brings us into everyone's favorite topic, the idea of unit vectors. So that's how you add things together. But we're working towards something called the unit vector notation, which is going to be very important for solving these systems. Unit vectors are going to be they're defined as vectors of magnitude 1, and they outline a space. So for Cartesian coordinates, they outline X, Y, and Z. So they will give you a space in which your physical event is occurring. If it's spherical space, your unit vectors are going to be rho, theta, and phi. Now, notice how they're written. You see the little hat on those? That's going to denote a unit vector. And I'll show you how that works in a couple minutes. So let's say we had unit vectors are going to be these little tiny infinitesimal vectors. And so the unit vector outlining the X dimension, that is your I hat direction. So when you start thinking of directionality, I hat is going to be your X direction. Now, in some textbooks, instead of I hat, J hat, you'll see X hat, Y hat. It's the same thing. It's okay. So you could either do X hat, which is more I hat, which is more traditional. You could do X hat, same thing. If you don't want to remember I and J, just use X and Y, just put the hat on them. Same thing if I'm doing an itty bitty little infinitesimal vector in that direction. That's either J hat or Y hat. So these unit vectors are going to denote the direction you're going in. So this unit vector notation or vector component form is how I'm going to want to see a lot of your work done. So let's say we have vector. We're just going to do an electric field vector. And it has components EX and EY. The way we write this, your vector component form, is we're going to take our component EX, and it's going to be in the I hat direction. Then it's going to be plus EY, and that's in the J hat direction. This is your vector component form. And don't, and just at this point, don't think you can add X and Y together. The unit vectors are limiting those from being able to interact with each other. Remember, EX and EY exist orthogonally to each other. They, for right now, the best way to understand that is perpendicularly. They have orthogonal essentially means there's no overlap between the two. Therefore, they can't add together. They're not actually dimensionally aware of each other. That'd be like, imagine this room is filled with beings that live in the fourth dimension. You're not aware of them because you don't live there. They what? They would be, yes, because you're a three-dimensional being and you're aware of both of those unit vectors. They're not aware of each other or you. This is it. No, I'm not talking like in Harry Potter. No, no. And if you're going to quote, if you're going to talk about Harry Potter, do it correctly. Those were thestrals, and he was only able to see them because he had experienced death. So this works more like a wormhole. Dimensionality works more like a wormhole. For lack of a better way of putting it, yes. Okay. Now, this can also be written as so you can use the X hat and Y hat if you want to. I don't really care which one you choose. This is just your vector component form. How do you put these together? Like, let's say you have components EX and negative EY. Well, if your positive and negative signs are going to go into the vector component form. So this electric field would be EX I hat minus EY J hat. Same thing if we had negative EX and positive EY. So yeah, you're just going to transfer in the positive and negative signs into your vector component form. Now, how does this look if we're adding or subtracting two vectors? Okay, well, we're going to have, and we're building up to something called superposition. Yep, superposition. Because energy fields, wave fields will overlap each other and interfere to form a new type of field. Not a new type of field. They're going to interact. So let's say we have electric field 1. And we have, in vector component form, electric field 1. And then we have electric field 2. Okay. Now we're going to add these vectors. Your total electric field will end up being E1 plus E2. And what this is going to look like is now we're going to take the components E1x plus E2x, and that will be your new I hat. Plus, and then you're going to have E1y plus E2y, and that's going to be your new J hat. So just like we talked about adding the components together, you're doing that here. You're adding the two X components, you're adding the two Y components, and you're putting those in the place of the new I hat and J hat. What about subtraction? So just like before, now this is going to be E1 x hat minus E2 x, and that's going to be your, oopsies. That's going to be your I hat direction. E1 y minus E2 y, and that's going to be your J hat direction. You're the only ones that have ever had a hard time keeping up, though. Did you? Okay, well, so there goes that theory. Okay. Yeah, you guys didn't complain.
Always find a thing different. There's difference.
Semantics. I do appreciate the way you work together in groups. Okay. So let's look at this exercise.
Already exercised this morning.
Yeah, I didn't, so let's do this.
Exercise.
Okay. We have two electric fields interacting at a point in space, okay? The first electric field has the components E1x and E1y that you see here. The second electric field has these components. So first off, write each of these vectors in vector component form. Find the total electric field at the point where they interact. Then we'll just call that point the origin. Find the magnitude of the total electric field and find the direction of the total electric field. Well, let's see, and find the direction of the total electric field in where it points. I didn't write that very well. Graph all the vectors. Now, so we're going to take the E1x, that's going to be 1.9 newtons per Coulomb, I hat, minus 2.3 newtons per Coulomb, J hat. E2 is going to be 2.0 newtons per Coulomb, I hat, plus 3.5 newtons per Coulomb, J hat. So there's both of those vectors in vector component form. Now, you could make a guess at the angles that these are at based off the relative magnitudes of x and y to each other. Now you can see E1 is going to be in the fourth quadrant. E2 is going to be in the first quadrant. And you can see, for example, you can look at relative sizes of x and y compared to each other and know that they're going to have to move in y further than they move in x. So you could get a basic idea of where they're at. You could also calculate the angles that they're all at. You're not told to do that until you get to the total electric field, but you could go ahead and do that. So I'll do it for one of them. So let's do E1. We'll say theta. So you see, we're just going to bring back in our formula for direction. Theta is going to be a negative 50.4 degrees. So that means you're going to get a vector. So if you went just corner to corner, that's 45. We're going to go just a little bit further than that. And that's going to be that angle there. Now, how did I know it was that angle? Well, so yeah, how do I know it's that angle? Right? Yep, so clockwise direction from the positive x-axis. Also, look at the relative sizes of x and y. The magnitude of y is larger than the magnitude of x, which means if it's going in x down further than it's going in y down further than it is going in x over, that larger angle has to be the one coming down from the x. It's greater than 45, so it has to be the larger angle. As we practice with this, you'll get better at it. The other E2, if you can work it out, goes up at about 60.3 degrees. So a little bit steeper. So now we want to work out E total. All righty. So now that we have the formula written out, well, my E1x is going to be 1.9. My E2x is going to be plus 2.0 newtons per Coulomb. That's my I hat. Plus my E1y. Now you remember my y direction for E1 is negative. So I have to bring that in there. Negative 2.3 newtons per Coulomb plus the E2y, which is 3.5 newtons per Coulomb J hat. And when I add those up, I get a total electric field that is 3.9 newtons per Coulomb I hat plus 1.2 newtons per Coulomb J hat. So first off, I already know that this total field is going to be a first quadrant vector. Why? Both positive. So let's go ahead and figure out the magnitude of this vector. So again, we're going to square both the components, add them together, and take the square root. So our magnitude, when you add that all up, is going to be about 4.08 newtons per Coulomb. And the magnitude is a scalar. Why? No direction. It's just a magnitude. Remember, your scalars are just your numbers. Then, what about the direction of this vector? Phi again, inverse tangent of y over x. Phi is going to come out to be 17.1 degrees. And so that's a positive angle, so it's going to go in which direction? Counterclockwise. We know it's first quadrant. This is a positive angle. So if I graph this, that's going to be there. So get used to this, get used to how we do this, because this is going to be the majority of your problem solving using this component notation. Again, things like vector component form or unit vector notation, those are vocabulary words. They both are going to refer to the same thing. Writing that vector equation in terms of its components using the unit vectors. And the last little thing to look at, multiplying and dividing vectors by whole numbers or any number at all. So I don't know. If I have, oopsies, my electric field, and let's say I want to multiply this by 3. If I told you that vector multiplication is distributive, what are you going to do? Yes, Liam, it does mean I'm going to distribute. What does that mean? So that's going to be 3 times the x component plus 3 times the y component, j hat. So again, you're going to take that number that the vector is multiplied by and just bring it in and multiply each component. So what about, let's say we have, so B, does anyone remember what B is? What physical reality is the B vector going to be this semester? Yep. Now let's say we're going to divide this by 4. We do the exact same thing. It's distributive. Distributive. It's a magnetic field. You could either divide by 4 or multiply by 1/4. It's the same thing. All righty. So it's like today you are going to have your first assignment. There will be vectors on it. I'm going to want to see certain things. So I want to see how you handle that when I write it. But nope, because I don't know where we're going to get to by the end of class. Everything we get to by the end of the week is fair game. There are other forms of vector multiplication. We'll talk about those when we get to them. So I found out last semester talking about them too early, nobody remembered them by the time we got to them. All right, let's move on to electric charge. Now, one thing that happens with charge that happened with energy is that it's conserved. So the total charge you start with in a system is the total charge you end with in a system. The charge that when we're working with charge in physics, it's either represented as Q or Q based off the situation. Little q is usually individual charges. Big Q is usually the entire charge of a system. Net charge, if you remember back to chemistry, you can think of your oxidation numbers. When you add those all together, whatever you end up with, that's the charge of your ion or your system. Same thing applies here. You can add together all your pluses, all your minuses, and get the total charge of the system. The elementary charge. Who remembers seeing this? The elementary charge is the charge of, like you've used it before. It's the charge of what? Protons and electrons. 1.602 times 10 to the negative 19th. What is C? Coulombs. That is your SI unit for charge. We do have a little bit of breakdown over here. One of them you're used to. What is that second one? It's 1 Coulomb is equal to 1 what? Nope, not angstrom. So J is usually what? Joules. Do you remember what we said V is going to be this semester? Volts. So 1 Coulomb is 1 joule per volt. Or what's another term electrically? What is the amps? Amps seconds. So amps times seconds.
Well, we had the electric times. We had our refrigerator went for the day. Whole mess when I got that. But we had the electric guy come over and there was a wire and the basement was glowing red.
Oh, that's not good.
Yeah, it wasn't good.
That's not good.
Like cherry red.
That's why you also have to be careful with what you plug into what charger. So it's like my computer for the school won't charge unless it's on. So like the big brick you get from Apple for your computer, that's like a 60-volt charger. However, if I plugged like my little Bluetooth speaker into that, it'd fry it because the Bluetooth speaker doesn't work. It doesn't really need the 60 volts. So you also have to make sure you know what you're plugging things into. That 60 volts is going to put a much greater potential difference on the circuitry of the speaker than it's designed for. And they're going to start to melt on the inside. It could be, yes. Okay. As we start to go through, we're going to be dealing with charges in different sizes. So I put the metric prefix list up here. Some that are going to be very common: microcoulomb, nanocoulomb. We don't really deal with pico. That micro, what is that little symbol on microcoulomb? U, the Greek letter U. Oh, you usually have to use some kind of text shortcut.
Every single time use that.
Do you use Apple or? Okay, so you're going to want to bring up the equation editor and type backslash intermediate. It will break for you. It's like that. It's like that. You can use LaTeX to actually shortcut a lot of your formulas, your math, your symbols. Now, we have some basic things up here. Kind of, that's for introduction to electric field lines. We'll talk about it more in depth. What's the difference between those two? One of them is an attractive electric field, the other one is repulsive. You notice that area of zero electric energy in the repulsive field? Now, theoretically, this is zero. We all know that there's still going to be some residual charges in there, but the two fields are going to repel each other. The attractive electric field, you see the field lines connecting. Of course, positive, negative repel, positive, negative attract. So this is just some general ideas. Also, again, which way do the fields go? Out of what into what? Out of positive and into negative. I need to come up with a problem that uses like yoctocoulombs. Just quectocoulombs. That'd be fun. Just watch people go, what the heck's a quectocoulomb? All right. So let's start let's do our first electric exercise, seeing how well your logic works. This one isn't going to use any theorems, but can you figure it out? You have 1 gram nugget of gold. It's electrically neutral. What would be its net charge after it has 1% of its electrons removed? Darn, how do you do that? 1% of what? Yep, which is how many? So it's neutral per what?
percentage.
Well, let's start there. 79 atoms per what? Each atom. We have 1 gram of this.
Result.
1 gram. Per mole. Now what number do we use? Yep, the avocado number. Yep. Because remember, that number is 1 mole of anything per mole. So okay. Oopsies. You use them enough, you should probably have a few of them memorized by this point. And what we said, we have 79 electrons per atom. So when we multiply all this up, it's going to give us 2.42 times 10 to the 23rd electrons. Now we're going to sweep away 1% of those. How do we figure that out? So then we're going to do 0.01. That is going to be 2.42 10 to the 21st electrons. Now, how do we really rationalize this out from here? I've swept away that many electrons. What charge will this 1 gram of gold have? Positive, because I did what? By removing electrons, I exposed what? To expose what? Protons. No, you have to do the math. You know what? If your logic takes you there when you're doing an assignment, you go ahead and put that on there, turn it in, and we'll see what the universe decides. Yeah, so here's the deal. We now have an imbalance of a total imbalance of 2.42 times 10 to the 21st. That's how many protons have been exposed. So how do I figure out the total charge of the 1 gram from that? Nope, I can use this number. I've swept away this many electrons, which means I've exposed how many protons? Nope. That'll tell you how many electrons are left, but all of those electrons that are left are neutralizing other protons. Yes. So that means I now have protons exposed, and each one of those it's just a little logic exercise to get at the start of the semester to get your brains working again. Per proton, which tells you that you're going to have a charge of about 388 coulombs. That's the shorthand for proton. Electron, proton, neutron. These are particle physics notations. I may ask you on your first quiz to tell me out of this list which one is the nucleon. Did you? Do what? It'd be a negative number, yes. Because the fundamental charge is either positive or negative based off proton or neutron, or electron. Neutrons don't have a charge. Yeah, particles in the nucleus. So if I put proton, electron, boson, the proton would be your answer.
And no, no, and neutron.
Neutrons and protons are your nucleons. Okay, conductors versus insulators. So look here. Here we have, this is something that I think you remember from chemistry. This is metallic bonding. What do you see there?
Yeah. I carry the whole electron.
Yeah, all of you organic people, what are those electrons doing? Yeah, so they're delocalized. This is metallic bonding. You get these the metal atoms will line up in a crystal structure, and then the electrons inside the metal start to flow as almost like a gas, an electron gas. That's why metals are so conductive. You touch them with any current, any potential difference, the electrons will realign real easy. Insulators, what do you see the differences here between the insulator and the conducting?
There's free electrons.
More free electrons in the conductor, so that means in the insulator, the electrons are what?
Localized.
If they're in an orbital and they're stuck there, in what kind of state? Think of a negative energy. What kind of state? So negative energy is below the ionization. So the electron has to be given enough energy to escape. Bound state. You have to. I talked to you all about bound states in chemistry.
Well, that was so big.
Okay, so
Yeah, old now.
the insulator, it has more electrons bound in their orbitals than the conductor does.
Bound means they're not outmost.
Well, they are bound means that they are forced into they're connected to their nucleus. The electric charge of their nucleus holds the electron tight. The electron can't just move around freely.
So, and the model itself is And
Even inside,
are they in that
even
section?
yes, even inside things, they has that zero energy positive energy, they're still bound. Like your electrons that are given ionization energy, will achieve positive energy and they will into the state. You talk them down. Yeah. Some materials could be charged by rubbing with other materials. So like you could have like the plastic rod, you can actually remove electrons from the plastic, right? They'll just take them off. All right. So we can charge objects in two ways. The first way to charge an object is by conduction. What happens here in conduction? Your positively charged rod comes in, your neutral metal sphere. Do you see the word touching in there? That's the key to conduction. The two pieces have to touch each other. And when they touch each other, negative charges from the sphere are going to jump to the rod. And since it's usually plastic or whatnot, it doesn't come down. So the rod will take those charges away. Now the sphere has an overall positive charge because it also of its electrons. That's conduction. Versus induction. You can charge by induction. What do you see here? They don't touch, so that's key. So your metal sphere, you talk about the metal having like the electron cloud in there. You see I bring this charge rod close to it. What happens to that metal sphere? It becomes what? No, look at it. You separate, which means it becomes what? What's the vocabulary word? Let's see, let's say it has its own moment, which means it's what? Polarized. Mhm. So you bring the charge rod close, it polarizes the spheres. Then once you polarize the spheres, you connect it to the ground. Once you connect it to the ground, what's going to happen? What disappears from that sphere when I connect it to the ground? Positive charges. So that means electrons came from the ground up to the sphere to neutralize some of that positive area, because the ground can only see this side of the sphere. And so it's going to go, well, I'm going to neutralize that positive energy, and so electrons come out. And so then what I do is I disconnect it from the ground, and then once I remove the positive sphere, the positively charged rod, then the charges in the sphere will space back out, but now it'll be negatively charged overall. Overall charge will be negative. So this is charging by induction.
So if you bring a negative rod, we'll reverse this.
Yep. And so then at that point, when you connect the ground, electrons will leave the sphere in the ground. Yes. Well, after you charge it and it takes a lot away, and the charge is rebalanced inside the metal. Since you had positive charge neutralized by gaining electrons from the ground, you now have an overall negatively charged conductor. Yes. The difference really is conduction is touching, induction is not touching. Induction just takes a process. There's not an inductor or a conductor. What are you talking about? In one of them you touch the two materials, and electrons dump there. The other one involves polarizing one of the using a charge to polarize one of the materials, connect it to the ground, allow charges on that material to neutralize the ground, disconnect it from the ground, and then you take away the charge, which is to polarize it, it's now overall charge. Well, this follow this four-step process. You Coulomb's law. Our first physical law. The electric force between two charges is going to be K, Q1, Q2 over R squared. What do you think R is in this case? Radius. Nope. And I put this mean back in because y'all gave me hell about it last semester. It is. The distance separating the charges. And yes, I put this back in because I had some dose premises coming last semester that will go.
I just asked you a question.
So.
Okay.
Well, that thing's cute, so I don't care. So let's think about this. Let's say we have okay, so here we have a positive charge and a negative charge. Okay. These two are going to attract each other. So let's think of it again, how we write these. So this force here is 1, 2. This force here is 2, 1. How do we read those? Yep. So like that force 1, 2 is the force applied to 1 by charge 2. The F21 is the force on charge 2 applied by charge 1. And then based off what we learned last semester, force 2, 1 equals what? Negative force 1, 2. So Coulomb's law works very much like Newton's laws. And again, if these were both positive, the force vectors would point the other way because it's going to repel.
Well, sometimes.
Yes. You didn't get this yet. Uh-huh. You see the application of the micro Coulomb in this problem? Yep. So here's the thing. We have point charges arranged like this. Find the magnitude and direction of the electric force on charge 3 due to charges 1 and 2. Okay, so the first thing I'm going to note, I'm going to want to know this. Do you notice how eventually we're going to have, you see our right triangle there? So, because when we work with forces, we have to know the separation between the charges. And so that hypotenuse there is going to be the separation between 2 and 1. Well, I guess in this case, we won't really need it, but still, we will in the future. We'd call that R12. So let's think about the directions of these forces. The force on 3 caused by charge 2 is going to point which direction? Up. Why? Why does it go that way? Mm-hmm. That's force 3 too. What about the force on 3 by charge 1?
Gonna go.
Yep. Because positive, they're repulsive. And if we wanted to know, see, and here's the thing: when when one of your point charges sits on the point you're interested in, you don't even have to include it in the calculation. Well, we will for force on it, but you'll see what I mean. So let's see here for a second. What about them? No, we're not worried about right now. We're just worried about the force. Each one, they're all providing forces to each other simultaneously. Right now, we're only worried about the force on charge 3. So when we start looking at this, the first thing we're going to want to do, and I know we're almost done, but I want to get this started. We need to know the force 3-1 vector. So what we're going to start with, and I want you to pay attention to Coulomb's law. Your book does this with K. That's Coulomb's constant, okay? Usually you'll see it represented as 4 pi over epsilon 0, where epsilon 0 is the permittivity of a vacuum. You can think of it as the capacitance of space. So the first thing we're going to figure out, we need to know the magnitude of this force. So this one is going to be Q3, Q1 over, let's see, R31 squared. And so we'll start there next time. But from here, you would plug in numbers, you're going to get a magnitude of that force. You what? Well, in this case, R is given to you. Look at the graph. Your distance there between 3 and 2 is 0.5 meters.
So it's K Q3, right?
Yeah, Q3 times Q1 over R1 squared.
Then you plug in the using.
Mm-hmm. But you're gonna have to turn these into vectors in component form. Not yet.
Yeah,